Hi everyone, in this video I'm going to very informally give an introduction to the use of derivatives in economics. So in many economics courses you will use some calculus. Specifically you'll probably be asked to use and interpret derivatives, and derivatives are a subset of calculus. And by way of introduction, I'm going to connect derivatives with the more familiar concept of the slope of a function. So as discussed in some previous videos in this video series, the slope is a very useful piece of information. Specifically, the slope tells us about the change in the vertical axis variable given a 1 unit increase in the horizontal axis variable. So for instance, if I had this graph here, this tracks total cost with quantity on the horizontal axes. And so if I was told that the slope of this function is equal to 1/2, then this tells me that if I increase quantity by 1, then my total cost increases by 1/2. And in fact, as a brief aside, this measure is called marginal cost. So we would say if total cost behaved in this way, that the marginal cost would be equal to 1/2. And marginal cost is equal to the slope of total cost. So finding slopes and derivatives is intricately linked to finding marginal things. And that will be pretty important in your economics study. As also discussed previously, the task of finding the slope of a linear function is relatively straightforward. We just take rise over run between 2 points. So that's the change in the vertical axis variable, which in this case is total costs, divided by the change in the horizontal axis variable, which in this case is quantity. Now, more often than not, however, functions in economics have slopes that change, i.e. they are curved nonlinear lines. For instance, consider the following possible total cost diagram here. Now, the slope of the function here changes for different values of q. We would say that the slope will depend on what value of q we are at. You can see that it starts off quite steep and then gets flat and then gets steeper again. And so the slope of the function at q1 will be different from the slope of the function at q2, and in fact for all points here that would correspond to a different slope value. And this is where our calculus comes in. If we wanted to understand the slope of our total cost function here, let's say at point A, we would take the derivative, technically the first derivative of our total cost function that we have drawn here, and we often notate this dTc dq, the derivative of total cost with respect to quantity, or sometimes just Tc prime, and then we would evaluate that derivative at the value qa. Now, because the slope changes at every point here, this derivative evaluated at qa will essentially be telling us the slope of the straight line that is tangent to that point A. That's the red dotted line here. Now, to take the derivative of a function, we need to apply some rules that I will talk a little bit about in this video, but more in the next videos. Just conceptually though, I said before that we find the slope of a straight line by taking 2 points along our line and taking rise over run. Well, we could think about approximating the slope of this function at point A by taking rise over run in the vicinity of point A. That would be more like an approximation. So for instance, we could do it at here. And if we took rise over run between these 2 points, we're essentially finding the slope of the line that is the secant that intersects those 2 points there. And what you'll find is that the closer that we take our rise over run, so the smaller the interval between our 2 points that we take as rise over run, the more accurate the approximation will be. And actually, when we take the derivative, we're going to narrow the gap between these 2 points so much that basically we're taking that rise over run changes to be in terms of an infinitesimally small change. So you can see that as I narrow the distance between rise over run, our slope gets more accurate. When we take the derivative, we're considering these discrete changes as not really discrete at all. We're taking them to be infinitesimally small. So we're evaluating them at a single point. It's like an instantaneous change, which is then, as I said before, to essentially be finding the slope of the line that is exactly tangent to our point that we're interested in. Now here then, instead of triangles, which indicates discrete changes, when we notate what we've done, instead of the change in total cost over the change in quantity, or the change in our vertical axis variable over the change in the horizontal axis variable, we're going to use d's, and that means derivative, so infinitesimally small changes instead of those large triangles. Or, as I said before, sometimes we just use tc prime or tc prime of q. So that's conceptually what's happening when we're taking the derivative. It's the same idea as rise over run, except we're not thinking about discrete changes. We're going to think about very, very small, infinitesimally small marginal changes. All right, so that's what's going on in the background. There are a few rules to learn in order to learn how to take the derivative of different types of functions, and I'll do that over the next few videos. Before then, let's just go back to a function that I looked at in one of my previous videos in this series. If you saw the introduction to nonlinear equations, we sketched y is equal to x squared, and we found that it looked like this. And so now I'm just going to find the derivative and demonstrate what I've just discussed. So if we have a look at the slope of this function, we can see, well, for negative values of x, the slope is decreasing, so the slope is negative. And actually it gets flatter and flatter as we move towards 0, as x increases, becomes less negative. And then at 0, it kind of turns right around, and then the slope starts to get positive again where x is positive, and it gets steeper and steeper and steeper as x increases. All right, well, just for demonstration, if I wanted to take the derivative of this function, I would take y is equal to x squared. That is the equation of this function here. So I would take the derivative of y with respect to x. And I would take the 2 that's on the exponent here, and I'm going to bring it out the front. That will multiply our function. And then I would take 1 off the exponent. So this is a rule called the power rule. I'll discuss it more in the next video. It's probably the most common rule that you'll be asked to use. So dy dx then is 2 times x to the power of 2 minus 1, which is just 2 to the power of x to the power of 1, or just 2x. So that's our derivative. All right, well, what does it tell us? How do we use it? Well, then we can think, if we just take a point, what if x was equal to negative 2? What can you tell me about the slope at that particular point? Well, we would sub in x is equal to negative 2 into our derivative, into our dy dx. Well, that would be 2 times negative 2, negative 4. So we're being told here that when x is equal to negative 2 at that particular point, the slope of the straight line that is tangent to the curve at x is equal to negative 2 is negative 4. So we have a negative slope when x is negative, as we described before. And you can actually see that dy dx will get smaller in absolute value as x gets closer to 0. And that's happening because the slope is getting flatter. So if x was equal to negative 1, dy dx, how y is changing as x changes by a smaller marginal amount is 2 times negative 1, so negative 2. So we're getting flatter than negative 4. Let's check what happens at x is equal to 0. This is where our function turns. And so dy dx here, how y is changing as x changes at that very point is 2 times 0, which is 0. And this makes sense. At that turning point, our function is neither decreasing or increasing. So the slope is 0. And so our dy dx is giving us all the right answers here. Let's check another point, maybe where x is positive, so x is equal to 3, dy dx is equal to 2 times 3, so 6. Here, as we predicted, as we described, the slope gets positive and steeper. And it is steeper relative to lower x's, so if you checked it, x is equal to 2 or x is equal to 1. Now, lastly, we said before that the slope of total cost is equal to marginal cost. And in a similar way, we're going to say that the derivative of total cost is equal to marginal cost. And this is a pattern that you'll see in economics. If we have a total revenue, total of something, we can find the marginal version of that by taking the derivative of the total function. All right, so that's my introduction to the use of derivatives in economics. Now, there is more to say here, of course. For the purposes of introduction, for those who are really new to all of this stuff, I'm going to leave it here for now. In the next videos, I'm going to go through the various rules that we use in order to take the derivative of different types of functions. As always, thanks so much for watching my content. If you would like written notes to help you on your journey, or even just to support this channel to help me make more videos, you can visit my store. The notes on beginner mathematics skills for economics students include lots of practice questions with solutions, which can really help solidify your understanding of the skills discussed in these videos. Also, these videos have helped. Please like and subscribe, comment below, share, all of that. It all helps. Any feedback also super welcome. Thank you so much for watching my stuff. Have a great day, everyone.